Hello and welcome. Today we're going to look at a Leaving Cert question from the 2006 honours paper on the topic of Joules Law. This question was interesting from the point of view that rather than give students data and ask them to plot a graph, it actually gave the graph as part of the question and asked students to interpret the graph and do some calculations from it. But before we start this question, it would be a very good idea to revise our ideas of what Joules Law is actually about. Now, Joules Law is most commonly stated in this form. The power of a heating coil or the power of a conductor is directly proportional to the current squared that's passing through it. Power, of course, is measured in units called joules per second, which of course is equal to a watt. Current obviously is measured in units known as amps. However, because it's quite difficult to actually measure the power of a heating coil, in the Leaving Cert it is accepted that if you prove that the rise in temperature caused by this heating coil when you're using a fixed mass of water and the current is flowing for a fixed time will also be directly proportional to the current squared. So whereas this is the exact definition of Joules Law, and that's what you should use if you're asked what is Joules Law in a Leaving Cert question, in the experiment we actually proved the relationship rise in temperature is directly proportional to current squared. Rise in temperature, of course, is where we're using a fixed mass of water and the current is allowed to flow for a fixed length of time. Now getting back to the actual question. Question 4, Leaving Cert paper 2006. In an experiment to verify Joules Law, a student passed a current through a heating coil in a calorimeter containing a fixed mass of water, and later on in the question we're told that fixed mass of water is 90 grams or 0.090 kilograms, kilogram being the standard unit of mass, and measured the rise in temperature delta theta for a series of different values of the current. The student allowed the current to flow for 3 minutes in each case. 3 minutes with 60 seconds in each minute is 180 seconds, second being the standard unit of time. They give a graph. The graph is of rise in temperature in Kelvin against current squared in amps squared. Interested note, the graph is a straight line, but in that Leaving Cert paper somebody made a mistake. The graph did not actually pass through the origin. However, in the correcting that year, they accepted the fact that the graph should have passed through the origin, and if students refer to that, they were not penalized. The question continues. It says, describe with the aid of a label diagram how the student arranged the apparatus. That means don't just give a label diagram, try to give a little bit of detail as well. Why was a fixed mass of water used throughout this experiment? Explain how the graph above verifies Joules Law, and a little bit of calculation required then. So let's break this question down into its various component parts. The first part, describe with the aid of a label diagram how the student arranged the apparatus. Well, obviously you will need a heating coil heating water in a copper calorimeter. You will need a ammeter to measure the current flowing through the circuit, and you will need a thermometer to measure the rise in temperature of the water. I've also included some lagging to prevent heat loss from the calorimeter to the surroundings, and a variable resistor in order to vary the current as we do each run of the experiment. One thing that's often left out by students and is required generally in the Leaving Cert is a switch in the circuit somewhere. Generally switches are put in on the positive side of the circuit, and you can put in the switch there, but I think it's important to label it. Also, because in this experiment we're talking about the rise in temperature of the thermometer. Excuse me, I think that's a little error there. Because we're talking about the rise in temperature of the thermometer, it is important to put in some timing device, And if you just put in a digital timer, that would be important as well. So we've got the heating coil heated by the power supply. We know the current passing through the heating coil because it's measured on the ammeter. We know the rise in temperature of the water because it's measured on the thermometer. For the sake of completeness, because we're going to be measuring the mass of the water, you could put in a digital electronic balance as well. And that is the equipment and the diagram needed in this experiment. The second part of the question asked, why was a fixed mass of water used throughout this experiment? That's a standard enough question, and usually it's answered like this. You identify the variables that are in the experiment, and in this experiment, the two variables are the rise in temperature of the water and the current, or the current squared, if you want to call it that. And we want to investigate the relationship between these two variables, these two quantities. If we change the mass, we would be introducing a third variable. Also, you could say that a change in mass would actually change the rise in temperature. So maybe it's worth noting that as well. Also, to change the mass of water will also change the rise in temperature, so the theta values. The interesting part of the question was, it said the student drew a graph as shown. Explain how this graph verifies Joules' law. As we talked earlier, the graph is of rise in temperature in Kelvin, could be in degrees Celsius, it shows Kelvin, against the current squared in amps squared. There was a shocking error in this, that the graph did not actually, if you look at the plate closely, did not actually go through naught, did not actually go through the origin, but in the marking of that, it was considered that it should have, and any student who mentioned that wasn't penalized. So how does this graph verify Joules' law? This is another very standard kind of question. Well, you would always identify that the graph is a straight line passing through the origin. And this proves that whatever's on one axis is directly proportional to whatever's on the other axis. So in this case, you would say this shows that the rise in temperature is directly proportional to the current squared. And rise in temperature is taken as an indication of power, because power and rise in temperature, if you don't change time and mass, will be directly proportional. So that's considered to be equivalent to power. So the graph is a straight line through the origin, 3 marks, or 4 marks. This shows that the rise in temperature is directly proportional to the current squared, which effectively is Joules' law. I.e., that's Joules' law. That would be the next set of marks we put through. Now, clearly, the most challenging part of this question was the calculations at the end. And the question said, given that the mass of water in the calorimeter was 90 grams, we bring that to kilograms in each case, and assuming that all of the electrical energy supplied was absorbed by the water, that means we assume that there was no absorption of energy by the surroundings, or the calorimeter, or the thermometer, or anything like that. Makes the question a bit easier. Use the graph to determine the resistance of the heating coil. The specific capacity of water is 4,200 joules per kilogram per degree is given, and we were told earlier that the time that current flowed in each case was 3 minutes, which I brought to 180 seconds. Now, anytime you're given a graph like this and asked to do calculations from it, then obviously the slope of the graph will come into it. So without doing anything else, you can find the slope and calculate the slope of the graph. What you need to do to calculate the slope of a graph is identify 2 points that are on the graph. So you can't use original data points unless they're actually on the graph. And you can use any point on the graph even if it isn't an original data point. So the 2 points that I picked, and it's best to pick points that are pretty far apart, I picked 0, 0, and we've already mentioned that there was an error. The graph didn't go through 0, 0, but that was an error. It should have, and any graph you will get in the leaving cert from now on will definitely go through 0, 0 if it's meant to. So I called that point 0, 0, and I took that point there. Now that point is clearly 4.5 in the x-axis, the current squared axis, and it is between 60 and 18, and I reckon it was just under halfway, so I called it, after some deliberation, I called it 16.9. I'm calling this point x1, y1, this point x2, y2, and the standard formula, and always write down this formula because there are marks for it, to get the slope of the graph, y2 minus y1 over x2 minus x1, putting in those values there, and 16.9 divided by 4.5, using my calculator, it works out as 3.75, 5 repeating like that. That isn't, of course, what we're asked to get the resistance of the heating coil. That is simply the slope of the graph. If you want to put units on it, well, it is y over x. On the y-axis of the graph, there's degrees Celsius, or degrees Kelvin, and on the x is current squared, so it would be per amps squared. But normally units in intermediate answers like this are not required. Now we will continue with the main part of that question. Now we're told that all of the electrical energy supplied is absorbed as heat energy in the water. So we can say electrical energy supplied equals heat energy gained by the water. We can ignore absorption of heat energy by the calorimeter, thermometer, surroundings, etc. The heat energy gained by the water is very simple. It's mass by specific capacity by change in temperature. The electrical energy supplied by the water is resistance by current squared, which is the power, the energy supplied per second, by the number of seconds that the current is flowing, which we were told was 180 seconds. In this relationship here, of course, never lose sight of what we're looking for. We're looking for the resistance of the heating coil. We're given the mass, we're given the specific capacity, we're given the time. So just rearranging that formula, I end up with resistance equals mass, specific capacity by rise in temperature over time by current, which I brought across. Then we look at this here and we say, well, we've already calculated this rise in temperature, which was on the y-axis of the graph, over the current squared, which was on the x-axis of the graph. That is the slope of the graph, which we've already calculated as 3.755. So what we do is very simple now. We simply put in the values that we were given. We were told that the mass of the water was 90 grams. We were given the specific capacity of the water. We were told 3 minutes, which we bring to seconds, 180, multiplied by the slope of our graph, the slope we calculated earlier, and that turns out as a resistance of just under 7.9 ohms, 7.88 ohms, and that is the final answer there. Hopefully this was of some use to you. Thank you.